So I'd like to talk about the handout on background notes of inverse functions. We're going to just skim this material because there's only certain parts of it that we need for our trig class. And I certainly suggest you read over all the details in the text to help you understand these concepts. But here in this video, we're just going to hit certain of the most important points. The handout starts out with an introduction to composition of functions, and I won't read through this example here. We're going to go right to the exercise. Composition of functions occurs when one function is followed by another, and the example in the exercises that I give you two functions that we're working with. F of x equals x squared plus 5, and the other function in the exercise is g of x equals x plus 1 over x minus 1. And when one function is followed by another in function notation, we write something similar to an A here. I'm going to write copy down f of g of 2 we want to calculate. So in this composition where one function is followed by another, there's always an inside function that goes first, followed by an outside function. We think of working our way from the inside to the outside. So in A, I want to calculate g of 2 first. I can actually figure that out on the side. G of 2 is 2 plus 1 over 2 minus 1. That's 3 over 1, or 3. So that g of 2 inside the f parentheses here, I can replace with the value 3. G of 2 is equal to 3. So that g of 2 I calculated is equal to 3. Now, 3 is an output of the g function, but in this composition, 3 becomes an input for the f function. So I now apply the f function to 3, which means I square 3 and add 5. 9 plus 5 is 14. There's f of g of 2. Now let's just do one more example. I want to write down, not B, actually. I want to jump to C. F of g of x. Let's not work with actual numbers, but try to describe this using the function expressions. And when I have a function expression inside parentheses, I can just recopy that function expression. So inside here, for g of x, I can write x plus 1 over x minus 1. And now I have to apply the outside function f to what's inside parentheses. Sometimes I like to think of functions in this way. Over here on the side, I'm going to write f of a box is equal to box squared plus 5. I'm just writing a box in place of the x. The function isn't really all about x. It's all about a rule for what to do with what's inside parentheses. The function f really just says take whatever inside parentheses, square it, and add 5. So if, like right here, I happen to have x plus 1 over x minus 1 inside parentheses, then I have to take x plus 1 over x minus 1 and square it. That means square it inside parentheses here and add 5. And there, I'm not going to simplify this any further. That's not really our point here. We just want to be able to see how we get this new expression by making the composition of f with g. G on the inside, f on the outside. Now, all the answers to these exercises are at the end of the handout, so you can work more on your own and check your results. Second page. Now let's start talking about inverse function. If a function f is a one-to-one function, we can define a new function by reversing the arrows of the correspondence. The new function is called the inverse function of f. So let's look at a few examples with these arrow diagrams that we considered earlier in the course when we were first talking about functions. Suppose f is a function that takes any number and multiplies by 5. So if we think of 1, 2, 3, 4, 5 as some numbers in the domain of f, when we multiply by 5, 1 times 5 is 5, 2 times 5 is 10, so on and so forth. We get 5, 10, 15, 20, 25, some numbers in the range of f. The inverse function of f reverses that process, takes any number, and divides by 5. Visually, we can just point the arrows in the reverse direction, so the 5, 10, 15, 20, 25 box becomes the domain of the inverse, and the 1, 2, 3, 4, 5, the numbers we get after we divide by 5, are values in the range of the inverse. Another example we looked at, an example we looked at earlier had to do with ID numbers of students. Every student has an ID number. So we took up student names were in the domain, ID numbers were in the range of that function. If we change the direction of the arrows, we can say to every ID number there corresponds a student name. It's kind of the same information, we're just changing the direction of the relationship. We'd say that ID numbers are our domain values or inputs for the inverse, and the student names are our outputs or range values for the inverse. Now, not all functions have an inverse. In fact, if a function is not one-to-one, it's not going to have an inverse. Let's look at another one of these arrow diagrams we had earlier. We talked about postal zip code of primary residence of students. If we try to change the direction of the arrows in that relationship, what happens is we have here with 94112, we have several arrows starting at the same zip code. So that's not allowed for a function. We can't have one domain value that corresponds to multiple range values. So while the original relationship was a function, the reverse relationship here is not a function. And it's because the original relationship was not a one-to-one function. So the way we define an inverse is if we have a one-to-one function f with domain A and range B, x corresponds to x in the domain corresponds to y equals f of x in the range. The inverse is going to be the function represented by changing the direction of the arrow, by starting with a y value, which we will call a domain or input value, and the output is going to be the corresponding x, which we will call a range value. So we're just changing the direction of the relationship. Here we have a statement f inverse of y equals x whenever f of x equals y. And this is a statement that we're going to have to try to understand. Now I've gone ahead and I've introduced notation here where I've written this f with what looks like a -1 exponent. That is read f inverse. We do not say f to the -1 power. Unfortunately, f inverse does not mean 1 over f to the first power. F inverse does not have a negative exponent. A negative exponent. It's kind of too bad that we're using this exponent kind of notation to represent a new idea, but it really is a new and different idea. So this is crucial that we learn that this does not mean 1 over a function. And we got to get used to it. We got to get used to the fact that the -1 is written for this inverse relationship. So I want to get back up to what's written in the box. F inverse of y equals x. Whenever f of x equals y, the input for the f function is the output for the inverse. And the output for the f function becomes the input for the inverse. Now this seems kind of abstract, so let's go down to this exercise, which I think will help us out a little bit here. So if this just seems a little technical, let's try to bring it to life with this problem. Suppose f is a one-to-one function with some values given in the table below. So here's a table of values with x values and y values. Notice this table is like saying f of 1 is 8, f of 3 is 4, f of 7 is 2. That's a function notation way of expressing just the fact that this x goes with this y, this x with that y, this x with that y, correct? We want to find f inverse of 8, f inverse of 4, f inverse of 2. That's really what the problem is asking us. There's nothing to calculate here. This is just interpretation. And we're just going to write down the answers here. The output for the f function, like the y values for the f function, become the inputs for the inverse. And what is f inverse of 8 going to be? Well, that's just going to have output that was the input for f. So it's going to be 1. F of 3 is 4, so f inverse of 4 is 3. We're just turning the pair of numbers around. F of 7 is 2, so f inverse of 2 is 7. So to me, with very specific numbers, this example or this exercise illustrates that property that seems a little bit more abstract, written with x's and y's up above. So on the handout here I say, f inverse does not mean 1 over f. It's got nothing to do with negative exponents. And another way to kind of get an understanding of inverse is to think about points on a graph, how the graph of f and f inverse are related to each other. So here we have a statement: if AB is a point on the graph of f, then BA is a point on the graph of f inverse. If I take these same values from that exercise 2, here we're saying that 1, 8, 3, 4, 7, 2 are points on the graph of the function f, the original function f. These statements about f inverse are saying 8, 1, 4, 3, 2, 7 are points on the graph of f inverse. So if you just turn the coordinates around, you get, if you take points on the graph of f and turn the coordinates around, you get points on the graph of the inverse function. let's talk a little bit more about graphs here. Remember, we can use the horizontal line test to determine if a function is one-to-one from its graph. So, for instance, we know f of x equals x squared is not one-to-one because we can find horizontal lines that cross that graph at more than one point. So that function does not have an inverse. Another example is f of x equals x cubed. That function is one-to-one. It satisfies the horizontal line test. Horizontal lines cross it at most once. And so this function has an inverse, and we can use algebra to find it. Now, I'm not going to go through the algebra with you all here, because we're not going to have to do this type of calculation in our trig class. I just want you to see that when you go through that, the inverse function that we obtain is the cube root of x function, and its graph looks something like so. And I just want to say a bit about how we can think about the relationship between the graph of f of x equals x cubed and how it's related to the cube root. And I have a graph here. I'm just going to pull the camera out a little bit. So I just drew my own version of the graph of the y equals x cubed. And so here's the x-axis, here's the y. Like one point, I just picked one point to plot, to label here, 2, 8, because 2 cubed is 8. That's a point on the graph of this cube function. One way to see how the graph of this function and its inverse are related is to just interchange x and y. In fact, it's just related to this idea that the points on the graph of the inverse have the reverse coordinates to points on the graph of the original function. So visually, that's like interchanging the x's and y's. It's like interchanging the x and y axis. It's like I want to change their positions. Now, I can't just turn the picture sideways because I don't want negative values going off to the right. So if I try to interchange the x and y axes and keep positives to the right, positives going up, I actually have to turn my picture over. And if I turn it over, then I can get these values that were originally 10, 20, 30 on the y-axis. I can get them on the horizontal axis. And the 1, 2, 3 that were on the x-axis, I can switch them to the vertical axis. And I'm going to interchange my x and y. So now I'm at 10, 20, 30s on the x, 1, 2, 3 on the y. And the shape that I see is the shape of the cube root function, the inverse of the cube. This point has coordinates 8, 2. On the other side, it was the point 2, 8. So I'm actually just taking this exact same shape, flipping it over, and in this reverse view on the back side of this sheet, I see this graph of the cube root after I've switched the two axes, right? So I didn't just flip it, I had to flip it and also make sure the one axis is going this way, the other axis is that way. So it's this kind of flipping and turning way that you can imagine switching the x and y coordinates to see the relationship between the graph of a function and its inverse. Let's go back to the handout now. So one technical thing we are going to have to talk about is something called restricting the domain of a function to obtain a one-to-one function. If a function is not one-to-one, it may be possible to restrict the domain in order to create a new function that is one-to-one. And the new function will have an inverse. And an example of that is with f of x equals x squared. We've already seen that that function is not one-to-one, does not have an inverse. However, we can restrict the domain of that function. And what I want to do is restrict the domain to the interval from 0 to infinity. So we're familiar with the parabola, that's the graph, the U-shape, that's a graph of f of x equals x squared. If we only take points that correspond to x being greater than or equal to 0, we get half of that parabola. So that's what I mean by restricting the domain to the interval from 0 to infinity. We're only taking this portion of the graph. That portion is 1 to 1. And that restricted domain graph will have an inverse. Its inverse is actually the square root function. The square root function can be thought of as half of a parabola on its side, right? The inverse of x squared with restricted domain. We're going to talk more about this domain restriction when we work with sine, cosine, and tangent. Okay, and then we've already observed that if AB is a point on the graph of f, then BA is a point on the graph of the inverse. There's another relationship about the graph of a function and its inverse described here. I showed you my flipping version where we flip a graph over to see the inverse. So I'm not going to say more about this. And just at the bottom, inverse and composition, to get back to that idea of composition of functions. Another way to think about how a function and its inverse are related is to compose them. If you compose f inverse with f, or f with f inverse, you're always going to get right back to x, right back to where you started from. And that should kind of make sense. Like if you multiply by 5 and then you divide by 5, you're right back to the number you started with. If you compose a function with its inverse, you're back to where you started, as long as you have values of x that were in the domain of the original function. So again, the next page has answers to the exercises if you want to do it. That's all I'm going to say about this handout on video. Next, we're going to start working with trigonometric functions and their inverses.